in the control area. It does process controls, and I'm very good at computer technology. And
okay, let me try again. I just want to swap.
okay. So if you want to have something work for you using MATLAB, go to MATLAB Central in the MathWorks. There are lots of codes contributed by Professor Paoloni that can be directly used by you solving your research problems. So we are very we believe that so not only in terms of theory but also in terms of application. So Professor Paoloni has the nice blend. Okay. So as shown in this talk. Enjoy. Okay, let's welcome.
Thank you very much for so kind introduction while I was trying to set up my computer. Let me briefly introduce myself. I'm living in a small country called Slovakia. So basically, some people use it with Slovenia, that is former part of Yugoslavia. So just to give you a picture, the place is not really unknown. You never heard about this, but it is not really unknown. The oldest city marathon in Europe is Košice Marathon, and it is the third oldest marathon in the world after Boston and Yonkers. And this year, Košice is the European capital of culture. The city is small size, I would say, something like 300,000 people there. According to CNN, this is one of the top 10 destinations for this year. There are things that you can really enjoy there. For example, these pictures are from my city, Yanchuan visited.
Yeah.
So we have nice center. Well, the projector is not very good. Even the opera, if you like, wooden churches and other nice pieces of architecture. Medieval things like this is a huge medieval castle in Slovakia, one of the largest in Europe. So also the university in Košice, where I live, was founded in 17th century. So we have a lot of things to show. If you would like to explore fractals, there are also fractals in the underground, in the caves, or on the ground, in the mountains. So everybody is welcome. And for today, I decided to speak about the tools that actually everybody can use, let me say, after leaving this one. So this is the topic of my talk. How could we create fractional order models for real objects? And of course, Professor Mainardi also indicated that it is possible to derive equations starting from microscopic viewpoint, and I expect that Nikolai Karabel will also speak about those things. But there is also a more trivial approach, like just explore a natural phenomenon and try to apply, how to say, a macroscopic viewpoint. And I have a couple of additions on the fly to Professor Mainardi's talk. He mentioned gamma function and beta function and so forth. So gamma function and beta function were introduced by Euler in his famous paper dated back 1738. And this is a very interesting piece of work. Just think, he introduced gamma function, beta function there. He evaluated fractional order derivatives of the power function x to n. He evaluated fractional order derivatives, gave the first textbook example of half-order derivative of x that is perfectly correct from today's viewpoint. And even more, in that paper he also wrote, but did not solve correctly, the fractional differential equation. But when I had some reasons to return to those papers, and when I read that paper, I realized that something is missing there. Nothing like the and, just stop somewhere in the middle. So I wrote, in addition to Euler's paper, just demonstrating that using his tool to consider also fractional order integrations and discover mutually inverse relationship between fractional derivatives and integrals. So I think he really could do everything in that one paper. So gamma function, beta function, examples of fractional differentiation, and also he could obtain complete picture. And I wrote a short paper on this and devoted it to 70th anniversary of Professor Merced. So you can go and check in the Journal of Fractional Calculus and Applied Analysis. Also, Professor Merced was speaking about distributed order operators, and in our recent work with Zhuang Zhao, Dr. Chen, we discuss distributed order dynamic systems, stability, numerical simulation perspective. And here is a very simple picture illustrating distributed order derivatives. So this is the formula that you already have seen. We have to add also some normalization condition for the weight function phi of alpha. And if we consider all those alpha as different, then we have different kinds of relaxations for individuals of some population. And the number of individuals, the distribution of the individuals across the population is given by the function alpha. So this is, in some sense, a useful tool that for thinking about distributed order derivatives. I will speak about some tools where I will concentrate on using Caputo fractional derivatives. Also, you have seen this definition, but this is Professor Caputo himself. After he wrote his famous definition on the blackboard last year in September in Italy, we were present at that lecture. So now about the topic itself. How do we usually create the models? I selected the example of the capacitor theory, and here is the story. Professor Svante Westerlund from Sweden worked for many years. He told me that he worked for more than 30 years in capacitor industry. And he discovered again, he observed during his industrial practice that the theory doesn't correspond to what happens in real life. He was looking for some better description and arrived actually at the model which involves fractional order derivatives. But how? What did he have to do in order to justify his approach? He came back to original measurements did by Curie in the end of 19th century, and we just fitted those data with a different curve. So he concluded that actually those data can be could be fitted with the power law, and the exponent is close to 1 but not equal to 1. So what happened in the classical case? There were some data, but people didn't know about power law and fractional calculus. So the closest curve to fit the data was just 1 over t. And this is how the classical capacitor theory appeared, and that's all. So he came with his student later and collaborator Lars Ekström. He came to that idea and actually created a fractional order capacitor model. And what are the consequences? If you are going to design an electrical circuit containing resistors and capacitors and inductances and so forth, basically you work with basic elements. This is a kind of Lego. And if you take integer order model for a capacitor, then it will go into those equations that you obtain, and those equations will be of integer order. If your capacitor is modeled with fractional orders, then the resulting equations will also contain fractional orders. Clear. So he continued, and there is also a very nice paper in Physical Scripta under the title "That Matter Has Memory." So this is actually a very simple and useful approach. You have data, you have to think about those data and create a model of your elementary process or an elementary object. Then you apply various laws like preservation of energy, preservation of moment, and so forth, and then you obtain higher order differential equations or their systems. So what usually happens? What does happen usually? You have some data. Okay, look at some experimental data. Which ideas do we have when we look at some point? To fit by a line, by a parabola, or so forth. If we cannot find a good thing, we can say, okay, this is the error. This is also the error. Remove, forget it. Not always it is possible. So basically, we collect some data and think about the shape that we can observe there, and then play with parameters, with some coefficients, to adjust the shape as close as possible to the data. Okay, how many functions do we know? How many combinations of them can we recall when we look at some set of data? Any idea? Of course, we can see here a line, a parabola, or what, I don't know what else. And as we decide to use some particular fit, then we can use it in some way. Like in the capacitor case, the fit was 1 over, or a constant over T, and the result was the classical capacitor. If you get another fit, 1 over T to power alpha, then the result in theory is fractional for the capacitor. And, okay, those fitting curves can be used as for interpolation, for extrapolation, and also for creating those models of elementary processes and objects. Okay, this is also a very fresh example from last week. Here are the data. Yeah? The nature says, okay, we can model those data. We can model those data with straight lines. Okay, is this line good? There are other lines. So there must be some criteria to judge which fit is good and which is not. But basically, here we can say, okay, the nature says those seagulls are more or less at the same line. There is also some reason, because they are looking for food. They were waiting for some crabs and mussels. And naturally, they find them at the boundary of the moving water that discloses them. So, how many functions do we know at different periods? Linear interpolation, of course. People played with their geometry for a long time, for thousands of years in different countries. So, linear interpolation was already used by Babylonian astronomers around 4th century before Christ. Quadratic interpolation, or in general polynomial, was already known to Chinese. In around 5th or 6th century, trigonometrical interpolation. Also, Greeks, of course. Greeks played with triangles, with sines and cosines, and they already knew how to do this kind of interpolation. Later, for example, Kepler, when he studied the motion of planets, he actually fitted the data of observations using circles and ellipses in order to create his famous laws of motion of planets. And as science progressed, the exponential function came to the foreground. Why the exponential function also? Why exponential function was the one to came to the front. Look back. Newton-Leibniz, differential calculus, and then differential equations. Yeah? Then came Euler with an idea of fundamental solutions that involve exponential function. You recall characteristic equations with constant coefficients, yeah? And the roots, and everything is just exponential. So those basic physical laws and chemical laws at that stage of scientific development actually meant that it was the best tool those days. Exponential function came through differential equation, two models in physics, chemistry. A model for decay or for growth. And of course, its counterpart, logarithmic function, also appeared naturally. They are twins. So again, just briefly, linear, polynomial, trigonometric, exponential, all those functions look very different. Correct? Do you think so? They are relatives. So let's take a look. If we decide to use a linear function, this means that we fit the data using the solution of the second order differential equation. If we decide to use the exponential function, then it is the solution of the first order differential equation. If we go for sine and cosine for periodic things, second order again. If we see something like damped oscillations, second order, look at the right. It is all the same. So all those things on the right are just particular cases of second order differential equation with constant coefficient. So instead of postulating the type of the fitting function, it is possible to postulate the type of the differential equation to identify coefficients A, B, C in the best way in accordance to the chosen criteria. And what you get as the solution will be the best fit to your data. Basically, the data will tell you about the best shape, not your eyes and not your perception, but the data will auto-fit to the curve. Okay, do you know those two faces? Any idea? On the left, there is Mittag-Leffler, whose name already resonated here. On the right,
Donald News.
Donald News, whose software everybody uses, and Professor Maynard also used for his talk. And Knut, by the way, adored Mittag-Leffler also in the field of typography. He said that Acta Mathematica, journal founded by Mittag-Leffler, served him as an example of a beautiful mathematical typeset to create his tech system. And this is a part of Mittag-Leffler's paper where he introduces his Mittag-Leffler function with one parameter. And this is the typeset from 1903.
Like LaTeX.
Yeah, because actually Knut tried to
Emulate this.
emulate this. It is also nice to see here some strange notation for the gamma function, for example, but you easily get how to say used to this. So I like. So the Mittag-Leffler function was introduced by Mittag-Leffler in order to have functions with a special kind of behavior in infinity, not like exponential, but a little bit weaker. He was working in the field of complex variables. And he invented his function, but later, in 1954, Humbert and Agarwal introduced the second parameter. And this is what we need in the fractional calculus for applications. So this function with two parameters is wonderful because with its simple representation, it covers many functions as particular cases: exponential, hyperbolic, trigonometrical, error functions, and so forth. So many things that we knew as unrelated are just children of this. And if you need to compute, then of course there must be something like a button in your pocket calculator or in a computer. And this is a problem itself because even exponential function is not easily computable. And this is a generalization which brings some more troubles. So based on the works by Gorenflo, Luchko, and Luchko, we created a routine and published it long time ago and enhanced from time to time for computing the values of the Merced function. It is freely available at MATLAB Central File Exchange. Okay, so I told you that I will be using Caputo derivative, but it is good to remember that we have also those Riemann values, and I'd like to draw your attention to this thing: sequential fractional derivatives. Why they are important? Because when we derive differential equations, we actually take one differential relationship and substitute it into another. So we have derivative of the derivative. In the classical case, first order derivative of the first order derivative is equal to second order derivative. So in the fractional calculus it is not so. So basically it is safe to keep the order of repeated differentiations and to work with them carefully. Sometimes you can reduce them to one derivative, sometimes it is not possible, but just take a look at it. And how can we create basic models using the tool that I just mentioned, the Merced function? Okay, I'm using the reverse order. The title of my talk is Fitting Data Using Solutions of Fractional Differential Equations, okay? But now I do the reverse. I just use the Merced function and try to fit data using that function. If I succeed in this, then I will get something like this: y equal to some initial value times Merced. This is for Caputo. If this function gives me a good fit, then I describe my process using a fractional order reversation equation discussed by Professor Merced. And with this initial condition. So, okay, this means that we have something to start with and to substitute into further relationships. And using this idea, we also provided a toolbox for MATLAB, fitting data using the Merced function. So there are two parameters, alpha and beta, and we can obtain the fit that is equivalent to using Caputo derivatives or to using Riemann derivatives. What better suits your need? And with one function, we can obtain very different kinds of behavior. For example, like this, or like this. This is just a kind of exponential decay, more or less. These are oscillations and so forth. So, of course, you can play with this and verify that if you generate some data using the original function, introduce some noise, then do fitting, then you actually can restore the function. Alpha is more or less the same, beta is more or less the same. Difference is only due to the noise introduced. Another example of this kind, just to show that we can fit the complementary error function in the same way. If we take cosine and add noise and then try to restore or to fit the data, again we will get the same function basically with which we started. Sine, the same story. And this is also interesting. Done with oscillations, this is not the same formula, but the same behavior. This slide actually says that the metagrapher function really gives us a lot of power in fitting data using the same formula. The united form of presentation. Here is an example. Professor Mainardi mentioned that a couple of decades ago, nobody was interested in fractional calculus. Now everybody does fractional calculus. So this is the growth of a number of papers, and this is the growth of number of fields of applications. So now it is approaching 150. And these are the data from the Web of Science. So this is the exponential fit, just standard. And we can fit the data using the metagrapher, just for fun. Fractional calculus papers fitted by the metagrapher function. And of course, it is more accurate. It is more accurate in this case. So, I can only agree with what Professor Mainardi wrote and told you. The metagrapher function is the queen function of the fractional calculus, and we can consider it as a complete replacement exponential everywhere. Okay. In fractional differential equations, instead of exponential, it plays the most important role. Stability. Also, Professor Mainardi mentioned that the asymptotics of the metagrapher covers actually exponential and power law. So we tried to use this in introducing metagrapher stability notion. So in stability, we also can replace exponential with metagrapher. In probability and statistics, it is used already for a long time, again for the same reason. Just think about the role of the exponential function in probability and statistics, like Gaussian and so forth. Replace Gaussian with metagrapher, and everything is clear. And also, fitting of experimental data in order to create usable models is basically the topic of this presentation. But now I will show you an example of application. For this, we have to move from constant orders to variable orders. Okay, we worked at our department for relatively long period in the fractional order control. So this is a standard control rule. But what I want to tell you is that we have digital implementations of fractional order controllers, and we also have a lot of analog objects and controllers at our lab. And people in some other places, like here, University of Akron, work in other directions, FPGA implementation of half order, in this case, fractional order element. For analog realization, it is possible, as we did in 2004, it is 2002. As we did here, it is possible to use different kinds of circuits, but the underlying mathematics is the same. Continued fractions, expansions, and the values of the coefficients in the expansions tells us the value of the elements that we need for creating a fractional order element. One more approach was presented by Gary Bohannon, and this is the element called fractal. It was presented in 2005 for the first time, fractal. And this is an element that is actually just one piece, like an electrolytic capacitor, let me say, one piece, and it can be manufactured in order to provide desired fractional order. But there are also other works. Yesterday's edition was, we received a paper from KAUST, University in South Arabia, and Saudi Arabia, and this is another approach using graphene and nanotechnologies in order to obtain a fractional order capacitor. But the problem is that those one piece type capacitors are not stable so far. So, and as far as I know, the first study based on those observations was presented in this paper by Dr. Chen and Gary Bahana and Carl Koopmans and co-authors. Basically, they observed the aging of Gary Bahana's fractal, and this is a very nice piece of paper because you can find the exact data and measurements showing that with time, Bahana's fractal becomes a capacitor, just tends to 1. And okay, so this is an interesting thing because the element was designed as a constant order fractional capacitor, let me say, or fractional element. But with time, its order changes. So it is natural to think about variable order element. So for this we have to mention that the notion of variable order fractional differentiation and integration is already known. There is a very famous paper by Sampo and Ross, 1993, where they introduced such operators, and there are also numerous other variations on this topic, and a nice review is in the paper by Ramirez and Coimbra. But recently we published a paper on experimental demonstration of variable order behavior of those circuits that we actually created as constant order elements. We thought that those self-similar circuits, or ladder type circuits also, give us elements of constant fractional orders. They do, in some sense. But as we look at this better, we observe that there are some nice details to take into account and consider. So we had a system with such a fractional order element. For fractional order elements, we use the word fractans, like capacitance, resistance, inductance, fractans. And fractans is the term introduced by Alain Lemaitre, who is now in Paris, but he is also very famous in this field. So everybody can check our paper and use the same equipment to reproduce the reference. So what we did, we consider a domino ladder which should have the order 1/2, and with different precision, 60 or 130 steps. And we did very carefully measurements for this, and studied also in the frequency domain and in the time domain. In the frequency domain, of course, you can see that it really provides the behavior that we want in some frequency range. But outside of that frequency range, it is also not a half order. So even this is worth a remark. So now what we do with the time? We consider time intervals that are longer and longer and longer, and we feed the data using the detector function. So the result is interesting. So in both cases, in the initial time interval, those ladders behave exactly like half-order elements. But as time grows, the order changes and approaches 1 but never reaches 1. So this means that we can use those ladder type networks as fractional order elements with some caution. There are some limitations on applications, of course. So, my partial conclusion, because this is just one half of my talk, my partial conclusion at this point is that fitting data using the methodical function is a natural step in approximation. It gives us a kind of auto-tuning fitting. And basically, we do not need to guess about the shape of the curve. If we use this kind of fitting, then we obtain fractional order and variable order models for real systems. And what is a problem here, I have to read this because it is not very visible. If we use this kind of fitting, then we must think about reformulation of the basic laws in various fields of science. Physics, chemistry, and so on. This is a problem. This is a problem because you cannot touch the first stone in the wall. You have to rebuild everything. This is a problem. So one day perhaps this will be fully understood. Now there is, from time to time, everybody can observe some resistance. As soon as you go too deep into detail, there are some questions raised by that feeling. What will happen if we allow to break the classics? So collect your data, fit them using the mathematical function, get your fractional order model for your basic process or object, and continue. Okay. Now the second question. Which criterion can be used for fitting? Do you remember those seagulls? Still remember. In that picture, there was no any coordinate system, but you could still see a line. Could you? Sure. So, did you think in terms of least squares when you looked at those seagulls? No. You just looked at those things and said, okay, this is more or less good, more or less bad. You did not think in the way that actually people use as a standard method. So I would like to tell you some less known things about the method of least squares that is only present in experimental studies and optimization criteria and so forth. So, some history, why squares also, some alternative, some arguments in favor of the alternative, and some examples. Although least squares are usually attributed to Gauss, it is not so. The first publication on this was published by Adrien-Marie Legendre, French mathematician, in 1805, and later Gauss claimed that he knew this much earlier but did not publish because it is so elementary that it was not worth publishing. And Legendre wrote a letter with a very, I think, proper statement that claims of priority should not be made without a proof by previous publication. If you look at this work, it is only 1.5 pages. 1.5 pages. Later, I will try to mention why it happened exactly that way. So, until recent time, if you look for Legendre on the web, you could see this picture. But about 1.5 years ago, it was discovered that the picture is totally wrong. And this is a picture of some French politician of that time, but not of Adrien-Marie Legendre. And it was published in Notices of American Mathematical Society in December 2005. So 3 years ago, let me say. I was wrong. Time flows fast. Okay. So this is the real face and the only picture of Adrien-Marie Legendre. And this is a grotesque, a caricature. from the meeting of the French Academy of Sciences. On the right, there is Fourier. Fourier, his conduction, yeah? On the left, Adrien Marie. So, Gauss did not have a publication before Levander. He claimed he knew this, but he could not provide even his computational notes when they were lost. Strange to believe, hard to believe. His diary was unclear, and his colleagues to whom he referred apparently did not remember discussions with him on that. Some time ago, known people, Olbers and Bessel, known for his Bessel's function, suggested that they wrote that they saw Gauss using least square method. But it is already a long time ago, if you think, something like 30 years after that. German astronomer Schumacher suggested that he can repeat the calculations from the Gauss paper to demonstrate that the method was used. Gauss did not permit this. Gauss did not permit. He said his word should be enough. Later, no reason to ask for permission in 1981, Stigler repeated Gauss calculations and could not reproduce Gauss's results. Chelmich, Latvian mathematician, worked in US, reviewed the adjustments that Stigler suggested and still could not get the same result. So the question that we have here is, what method did Gauss use? Okay, so the question is what? And now I'm coming roughly to those seagulls. So you have some data. What could you see here? A line, an ellipse, or what? Okay, I would say a line. Or maybe another line. Or maybe still other line. Which one is better? How you can judge this? Okay, another set of points. An ellipse, maybe. Slightly different, maybe. Another one, maybe. How can you judge what is the best fit? Okay. The problem is that the line and the ellipse and parabolas and everything are not defined using formulas. Look back into geometry, they are defined by some rules. Formulas come to play only later when we introduce some coordinate system. And in some coordinate systems, we have some more or less simple equations. Yeah? This is in Cartesian. Okay. Can you write the equation of a straight line in polar coordinates of an arbitrary straight line? Not so easy. This is the ellipse in the canonical form. Okay, if you rotate the coordinate system, it is not so simple like here. If you will try to use other kind of coordinate system, there is a problem. So how did you judge the quality of fit? Of course, you internally evaluate proximity of the data points to the fitting curve. Proximity means some invariant quantity like distance. So what did Legendre do, and why it was so important that time? He realized that, of course, he should consider distances, but distances are difficult to process them. So he used a trick. He started considering vertical offsets in Cartesian coordinates, and instead of the distance, he considered the square of the distance, which is perfectly differentiable. And this is how he was able to use the tools of the differential calculus to solve the problem of finding a good fit to the data. So he did a wonderful trick. The only possible solution those days. No computers, no computational power, pencil and paper, and he was able to process huge sets of data, but started, let me say, reduced them to a system of two algebraic equations. Okay. So, but the problem here is an interesting one. So, this picture is ugly. This picture is ugly. Those squares have nothing to do in this picture from the point of some internal beauty. And let us change the viewpoint. So instead of just squaring, let us introduce some coefficient. I call it pi. And basically, based on the same vertical distances, we can consider not the squares as before, but circles, correct? And this set of circles is equivalent to those squares that we have seen, but this set of circles is not optimal. Everybody can see this. It could be optimal if all the circles are just touching the line. So basically, we are speaking about the shortest distances to the line. So instead of minimizing the squares of vertical offsets, we have to think about minimization of the maybe squares, maybe just the sum of distances of perpendicular orthogonal distances. So in this way, we arrive to something that is called orthogonal regression, and this is a nice point here, I think. First of all, it is natural. Second, this criterion is invariant with respect to the choice of coordinates. You can change the coordinate. If you change in the classical case, this is even more ugly than before. There is no problem with the fit. If you fit x against y or y against x, in the classical case you have two lines. But if you use orthogonal distance fitting, you have just one line in both cases. There is a famous Nieuwenveld example for that. So there are no problems with causality, because using the classical approach, we have to think what is independent variable and what is a dependent one. Sometimes it is not clear. For example, weight and height of a person. So what is, am I higher because my weight is, how to say, more, I weigh more, or maybe I weigh more because I'm high? Who can tell me? Who can prove? Clearly, the height and the weight are in mutual relationship, but what is the cause, what is the effect? And so forth. So, implementation of the orthogonal fitting can be done in any number of dimensions. So, the simplest case is, for example, here. You just observe, I call this a bumblebee, but you can imagine an aircraft or helicopter, it does not matter. And you have to guess where, in which direction it is moving. So you have some set of data, and you have to fit those data with a straight line. No chance to succeed with the classical least squares in 3D. No chance. The only way is to use orthogonal distance fitting. In the two-dimensional case, it is easily solvable. So we can obtain the corresponding equations. There are two possible solutions, and because the data are distributed, we can fit the data using lines that are perpendicular. So among those, we select the solution that gives the smaller value of the criterion. We applied this approach several times. One is just standard fitting of economic behavior. Okay, this is an interesting, I think, approach. So state of economy, everybody reads newspapers, and economy is in poor state. So what is the state of economy? We decided to use gross domestic product, unemployment, and inflation rates. So basically using state variables, and consider the state of economy as a point in that 3D space. So then what happens? Then we discovered that economies actually create trajectories in time, as time flows, trajectories of economies. This is the behavior. And it is interesting. The trajectories lie approximately in the same plane. For each economy, it is a different plane. So that was the conclusion that we obtained for Scandinavian countries, for Central European countries. And if we think in this way, then we can look at economies, national economies, differently. So we can find the centroid, we can have the normal vector for each economy. So we can compare them. In both cases, it is interesting. We obtained one country that is different from 3 others in those groups that are more or less in the same conditions, but the trends are different. And for solving this problem, we provide also a MATLAB routine available with MATLAB central parachain, which can give you a fit by a line or by a plane to the data that you supply. And okay, this is just a partial set of conclusions. We continued with our attempt. I spoke about trajectories, so now I have a chance to combine fractional order differential equations, their solutions, and fitting using orthogonal distance. So what did we do is the following. Again, we consider it a set of 3 Commonwealth countries, and tried to describe their behavior using solutions of a set of 3 differential equations of non-integer order. The orders are the same actually, I will tell you why. And some right-hand side. So why the orders here are the same? It came from numerical experiments. If we start parameter identification with different values of those orders, the output always contains the equal orders. So we do not have a theoretical justification for this, but the observation from numerous identification attempts is absolutely the same. The orders must be equal here. We have to look why. We have to look into the problem deeper. And these are the trajectories of those Commonwealth countries that we can. These curves are the result of the fit, and the fit is really good. So here are 2 papers that I mentioned, and this is the paper that I did not mention. We published a paper in the Journal of American Statistical Association called CHANCE, where we compare least squares and the method that we call least circles. I believe it is the first interpretation of orthogonal distance fitting in this way. So you can check. There are also MATLAB routines. You can go and check for my name and for the name of Professor Ivo Petrash from my university. And I think I finished earlier than I expected, more or less in time. And the pictures that I was using are also interesting. Did you like the pictures during my talk? They look strangely modern, but these are pictures by Giovanni Battista Braccelli from 1624. The digital version can be found in the Library of Congress. And what is especially surprising is this. Look, this is Adrien Legendre. I flipped the picture that I showed you. Look at this face, 1624, and look at this face 200 years later. Can you see the same features, absolutely the same look? I cannot explain this. But I enjoy observing this. Even the shape of this, the same. The eyes are the same. The nose. Even this smile, or not smiles, but the mouth. Everything is the same. Okay, so with little discovery of strange kind, I finish my talk. So thank you very much.
Well, we're quite behind our